Hello everyone, welcome to the video. Today we're going to talk about molecular dynamics simulation and specifically how to equilibrate a polymer system. So if you are watching this video, chances are you already have some experience with molecular dynamics simulations, but just in case you don't know what it is, basically MD simulations solve Newton's equation and produce a set of velocities and positions of the particles in your system, and then you can use that data to generate a little movie for your system. And so here's a simple example. So I'm just gonna put a bunch of particles in the box, and when I hit run, you can see that we have a little movie of like how these particles move around, right? We can even track some particles, and you can see that clearly those particles are interacting with each other, and there are just so many things that we can measure. For example, we can measure the diffusivity of those particles, which is like transport properties, and we can also measure the structure properties like radial distribution function, and there are just so many things we can do with these trajectory files, so which is very cool. So of course, in real world applications, we want to simulate much more complex system. Like one example would be polymer system, which is what we're going to talk about today. Polymer is everywhere, and everyone has some product that is made of polymer. So, but there are a bunch of challenges associated with running MD simulation for polymer system. So the first challenge in that we are going to encounter is how do you actually generate the initial configuration for a polymer system, right? So let me give you an example to show what I mean by that. So let's start with a very simple example like a water system. And the goal is to generate initial configuration for those water molecules. And to simplify the problem, let's just focus on putting this water molecules on this like single layer, and instead of the entire box. So we can just click, 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 and as long as we have space, it's very easy to put these molecules inside the box. So if you want to do it programmatically, you can just sample from a uniform distribution, and reject the atoms that are overlapping with each other. For example, if those molecules get too close to each other, the energy is going to be huge, and we don't want that to happen, right? So as you can see, it's like relatively easy to generate the initial positions for these water molecules. So now what about polymer system? So here we have a relatively long molecule, contains about 40 carbon atoms, but it's not like super long. It's just for demonstration purpose. So initially, just like the water system, like we have plenty of space, right? We can just put those molecules wherever we want them to be without much trouble. But as you can see, once we have like 4 molecules in the box, it already start to get a little bit difficult, right? Now we have 5 molecules in the box, it just becomes like impossible to squeeze another one, unless we sort of do some rotation, or if you are familiar with Monte Carlo simulation, we can generate some moves like rotate part of the chain, or there's just some expensive thing we can do. But the point is, it's not as easy as generating initial configuration for water molecules. So in practice, what people usually do is that they will start from a giant box, right? Let's say we want to put, let's say, 50 polymer chain inside a box, and the box is 50 angstrom, and then the target density is 1.068. We can pack this. So you can see the packing succeed, but we need to expand the box a little bit. So so in practice, what people would do is to start from a giant box, right? And then because we have a ton of space, it's relatively easy to put those molecules inside the box, but the density is low. So let's say you want to simulate your system under room temperature and pressure. And so obviously this configuration doesn't represent that because the density is just so low. So we have to do something to drive the system to the target state you want it to be. So in this video, we're just going to talk about how to actually achieve this. So the first method that I'm going to discuss comes from this paper. So basically this is about a certain polymer system named PIM1, and they're trying to study the intrinsic microporosity of that type of polymer, which is kind of interesting. And now let's go over the abstract very quickly. So the first part is, I think it's just some background knowledge. And if we continue reading, we can see that here they mention a detailed method for the generation of representative structures, which is exactly what we're trying to do here. So let's continue reading, scrolling down, and so you can see that this is the crazy polymer structure they're trying to simulate. Continue scroll down, and here you can see that the system is initially grown at a low density, right, which is exactly what we talked about before. This is just try to make sure that the atoms are not overlapping with each other, because for polymers it's kind of challenging to pack them efficiently. So let's continue reading, scrolling down. So here we have a detailed protocols of how they sort of drive the system to the target state. So like we mentioned before, the system started off from a low density initial structure, and the way that we actually drive the system to target state is by performing a series of short MD simulations, right? That's how we actually drive the system to the target state, is by performing MD simulations. Okay, so now let's take a look at the detailed protocols. So in the beginning, the first step is to run the simulation under MVT ensemble. So if you are not familiar with MVT ensemble, it basically means that we run MD simulations under a fixed volume and fixed temperature. So the volume is fixed, the temperature is fixed, and then we're going to sample from the specific distribution that is sampled from the MVT ensemble. So, and you can see that 600 Kelvin is kind of a high temperature, right? It's far above the normal glass transition temperature of like most of the polymers. So you might wonder, why do we want to run simulation at such a high temperature? I think the reason is because, let's say your initial structure is not ideal, and the system is kind of stuck at some local minima. And if you run the simulation under normal temperature, like 300 Kelvin, it might be hard for the system to get out of that local minima. So if you increase the temperature slightly, then it actually helps the system to get a lot of kinetic energy, and you get a lot of thermal kick. Your atom is gonna move around a lot more, and it's gonna help the system to relax. So I think it makes sense to run simulation initially at high temperature, and then the next step is to cool down the system to the normal room temperature, and then we're going to run for another 50 picosecond. So for step 1 and step 2, basically the volume of the system is fixed, which means that the density is still pretty low. We're not actually doing any work to increase the density of the system. So at step 3, you can see that we, instead of using MVT ensemble, we're now switching over to MPT ensemble. So the difference between MPT and MVT is that instead of fixing the volume, we are now fixing the pressure, which means that the volume of the system, of the box, is allowed to change, right? So if you can imagine that if we use a very, very, very high pressure to compress the box, the volume is going to decrease dramatically, right? That just make intuitive sense. If you want to compress something, you can apply pressure to it. So we are going to apply, we're going to run a simulation under MPT ensemble. The pressure that we use is 2% of Pmax. So what is Pmax? So now you can see that Pmax is 50,000 bar, which is a crazy high number, because at sea level the pressure is about 1 bar. So this is like a very, very high pressure, even though 2% of that is 1,000 bar, I think. So it's a very high pressure. So basically the goal here for step 3 is we want to like start like squeeze out the empty space in the box. And then you can see there's a pattern here, right? We run MPT and then we run MVT to kind of relax the structure a little bit more before we continue to compress the box. And now we go from 0.2% to 60%. So we're increasing the pressure we use to compress the box. And now continue doing MVT here for another 150 picosecond, and then we reach the Pmax, which is 50,000 bar. And so here we really, this is really high pressure, and you can imagine that every bit of empty space should be gone at this point. And so you might wondering, why do we like not directly use Pmax from the very beginning, right? We kind of use 2% of Pmax and 60% and then 100%. So why don't we just directly use like 50,000 from the beginning? So I think the reason is that initially your system is kind of not super stable. So if you go directly to Pmax, then it's possible that the atoms are going to move a lot, and then there's higher chance that some atoms will get too close to each other, and energy is going to be high, force is going to be high, and then the next thing you know, the atoms are just going to fly around, and your system will be destabilized, and then eventually your simulation is just going to die. So I think it makes sense to sort of gradually increase the pressure. And now you can see after step 9, the pressure sort of start to decrease, which makes sense, right? Because eventually we want our system to be at 1 bar. So we need to decrease the pressure from Pmax to 1 bar. So we need to decrease the pressure. And eventually we're going to run the MPT under 1 bar for 800 picoseconds, which is significantly longer than the previous steps, which makes sense because that is the actual target state that we want the system to be in. So it makes sense to sample longer. So now let's test what we just learned on the real polymer system. And so the polymer system that I pick is PMMA, and as you can see, we created a super long chain, contains about 2,000 atoms, which I think is long enough. So we generated 3 different samples just to create a error bar so that we can have a good uncertainty estimation. And let's open the full simulation. And we can print the atom comp. Here we can see about 12,000 atoms in the 12,000 atoms in the system. And we can now sort of copy paste some code in here so that you don't have to see me typing. So basically we just recreated the protocol that is that the paper sort of discussed about. Basically here we have two functions. One is MPT, one is MVT. You just return a dictionary and such that we can execute the protocol later. So the MPT takes 4 arguments: name of the protocol and pressure, temperature, how long we want to run the MPT ensemble. And for MVT we have similar structure, basically the name, temperature, and the time picoseconds. So we have 21 different steps. So the first step is we run the simulation on the T hot, which is I think is 600 Kelvin, right? Yeah, exactly. And then T cold, which is 300 Kelvin, 300 Kelvin, yes. And then we run MPT followed by MVP, the same pattern, and then we increase the pressure and basically repeat the whole pattern. So let's execute this cell, and you can sort of see that we have a really nice UI, displays all the different phases. So which is nice, and we can preview the script. So here's the actual LAMMPS script that we're gonna submit to the cloud, and you can see that we have all the different steps here. It looks good, and then we're going to submit jobs. Okay, so the second method we are going to talk about is inspired by this paper, which is high throughput molecular dynamic simulation and validation of thermal physical properties of polymers for various applications. So this paper is studying the thermal properties of polymers. So let's continue reading, go to the abstract. So basically this paper kind of calculate the glass transition temperatures of 315 polymers. So that is a lot of polymers. So they spend a lot of compute on this paper. Let's continue reading and figure out what is the protocol they use for calculating the glass transition temperature. Okay, here we go. The simulation protocol. So the protocol for TG calculation mimics the process of cooling from temperature while simultaneously tracking the density changes of the system. So the idea is very simple. Basically, they start from a high temperature. The system is at a high temperature, and they sort of slowly cool down the system. And so here's the exact number they use. They start from 1000 Kelvin and perform 5 nanoseconds of NPT-MD simulations at every 20 Kelvin step until 100 Kelvin. So they start the system at 1000 Kelvin, and they gradually cool down the system until it reaches 100 Kelvin. So for each step, the temperature for each step is like 20 Kelvin less than the previous step. And since we're not interested in calculating the glass transition temperature, but I think we can borrow the same protocol here, right? Because we also kind of want to cool down the system from the high temperature. And so we're interested in the equilibrium structure at 300 Kelvin, so we can cool down the system from the high temperature and sort of just get the structures that we need when it reaches 300 Kelvin. So the idea is pretty similar. Okay, so now I have the simulation page fully open. Let's take a look at how we can actually construct the protocol in this notebook. So basically, remember that the core idea is that we want to start the system from high temperature and run a simulation under MPT and gradually cool it down until it reaches the low temperature. In the paper, they sort of use the initial high temperature is like 1000 degrees, but here we're going to use 600. because we're not actually interested in the glass transition temperature, right? We're just interested in getting the equilibrium structure at 300 Kelvin. And so we're gonna pick a low temperature that is kind of close to 300 Kelvin. And here basically we construct an array, a NumPy array that contains all the temperature that we're gonna use in our MD simulations, and we then going to inverse the array because we want it to be a decreased order because we want to cool down the system, right? And and it's very straightforward for loop. We just loop through all the temperature in the system and add the phase to all the phases array, and we're going to run the simulation under MPT, and for each step we sort of run 3 nanoseconds instead of 5 nanoseconds because otherwise the compute cost is going to be so expensive. So before we starting the cool down process, we also need a initial equilibrium stage. So because we have such a huge box and there are a lot of empty space, so I wanted to sort of run MPT for a little bit to kind of squeeze out that space a little bit, and then run MPT to relax the structure for like 3 nanoseconds. And then we start the cool down process. Then let's take a look at the sort of the UI, and so everything looks good. We have like initial equilibrium stage and then start cooling down. Each stage takes like 3 nanoseconds, and everything looks good. We can look at the LAMMPS script that it automatically generated. Everything looks good. Cooling down 3 nanoseconds, so everything looks good. So we're going to submit the job to the cloud. Okay, it seems like all the simulations have completed. So now let's take a look at the final results. So I'm just going to first load the trajectory. So this simulation is the first method we talk about, like slow decompression and gradually increase the Pmax. Okay. So now we can first play the animation and see what it looks like. Okay. So you can see here we sort of increase the pressure, and eventually we are going to reach that 1 bar pressure. Okay, so basically the protocol is exactly what we expected. We have initial 2 steps, the equilibrium structure. So you can see during these 2 stages the density is still relatively low, right? 0.095, and then you can see as soon as we start running the MD simulation on the MPT, the density start to like increase dramatically. It's because we sort of apply pressure to the box, so the box start to shrinking, and the density will start to increase, right? And then we're going to run the MPT for a while, MVT for a while, then continue to compress the box. You can see that the density is going to increase. It sort of increased from like 0.291 all the way to 1.3. Now we're going to run the MVT again. So now you can see when we run the MVT, the density of the system is fixed. So now we reach the Pmax. So you can see the pressure is 50,000 bar, and the density is 1.425, which is much larger than the previous all stages. And then we're going to continue to run MVT. And then now I believe we are starting to cool down the system. And eventually we're going to run the simulation under MPT for 1 bar for 800 picoseconds, I think. So you can see the density sort of settles around 1.032. So let's take a look at the animation again. Yep, and yeah. Okay, so that's all. That's for the first sample. So so I run 3 different simulations for 3 different initial structure. Unfortunately, the second simulation failed because the atom is lost. So I mean, it sometimes happened, but it's okay. And this is another sample we have for the first method. We're just gonna take a look at this simulation also. It's going to take a while. You can see the exact same protocol. It's just a different initial configuration. Okay, let's play the animation. Very similar trend. Gradually settled down to 1.0063. So now you can see we run 2 different samples, 2 different simulations, exact same protocol, but the density that we get the final results are different, right? The previous density settles around 1.03, and this one is 1.06, right? And so here is a very important lesson, right? Which is, even though sometimes we run the simulation under the exact same protocol, but we still get different results because the initial configuration is different. And that's a good thing, because we want to have a sort of reasonable uncertainty of how accurate our number is, right? If we just run one simulation, as you can see, if we run a different one, the number we got might be completely different. And so it's very important that when we report our data, it's very important to also report the error bar. So, just so that the readers can get a sense of like how spread the error is. And if you want to decrease the error at the bar, decrease the width of the error bar, one thing you can do is to increase the number of samples you run. So for example, if you double the amount of simulation you run, then your error bar should decrease by square root of 2. So I mean, that is just the basic statistics. So whenever you read a paper and you see a number but you didn't see the error bar, and I'm not really sure that you should trust the number. So anyway, so this is the first method. Let's take a look at the second method that we talk about. So this is very straightforward. We just equilibrate the initial system and start cooling down the system all the way to 260 Kelvin. We are going to now look at the trajectory files. It's going to take a little bit longer because you can see that here this simulation takes like 54 nanoseconds, and previous one only takes about I think much less than that. Okay, so we have the trajectory files loaded. We're gonna play the animation. So gradually cool down, 500, 480, 460, 440. You can see the temperature. You can see the density gradually increase. Just interesting. So now you can see that because we're only interested in 300 Kelvin, the structure at 300 Kelvin, you can see that the density is around 1.056, which is sort of in between the number we got from the previous method. So I think they are kind of similar, I would say, but it's hard to say because we only have 2 samples. We can also load the other sample that we have. So previous simulation, the first method we only take 1.6 nanoseconds, and for the Second one, the total length is 54 nanoseconds, which is much longer. So we're gonna see the result in a second. There we go. Play the animation. The same thing. You can see the density gradually increase. Let's drag to 300 Kelvin. Okay, so you can see that the density is slightly higher than all the density that we reported before. This one settles around 1.072. So again, it's hard to tell which method gives the sort of the higher density because we only have 2 samples for each method. I believe for the experimental value, the experimental density for PMMA is around 1.18, I think. So you can see that our simulation did not reach that number. So there are multiple reasons for that. One probably is the force field is not good enough. So here we use the force field that we use is the I think is the open FF force field. So it might not be trained on polymer data. So that is one reason. Another reason is maybe we just don't have enough samples. We just don't have enough data. So that could be another reason. So, but you know, this kind of simulation is super expensive. It takes like multiple days just to get one single simulation finished. So if you have the compute resource, you certainly can run multiple singles, but here I'm just trying to demonstrate the whole process, and hopefully that's useful. Thank you so much for watching the video. All the files that I used and created in this video are available to download using the link below, and that includes the structure files for the polymer and all the LAMMPS control script for the 2 methods. And if you'd like to stay updated, feel free to subscribe to my channel and the blog. Links are below as well, and I've also included my email address, so don't hesitate to reach out with any questions or suggestions. I read every single email, and I will do my best to reply to all of them. Thank you so much. Have a great day.